Welcome to Knowledge Session Take 1. Today, we embark on a fascinating journey through 10 groundbreaking experiments that have shaped our understanding of the world. From the quest to uncover the mysteries of light and gravity, to the surprising discoveries that have revolutionized psychology and beyond, each of these experiments has left an indelible mark on the history of science. Ready to uncover the secrets of the universe? Let's begin. In 1887, physicist Albert A. Michelson and chemist Edward W. Morley set out to conduct an experiment that would forever change our understanding of the universe. Their goal was to detect the presence of ether, a hypothetical medium through which light waves were thought to travel. At the time, the ether theory was widely accepted by scientists as the explanation for how light propagated through space. Michelson and Morley used an interferometer, a highly sensitive device that splits a beam of light into two perpendicular paths, reflects them back, and then recombines them. The idea was that as the Earth moved through the ether, the speed of light and the direction of Earth's motion would differ from the speed of light perpendicular to it. This difference would create an interference pattern that could be measured. To their astonishment, the results of their experiment showed no difference in the speed of light in any direction. This null result contradicted the ether theory and left the scientific community puzzled. How could light travel through space without a medium? This groundbreaking result laid the foundation for Albert Einstein's theory of special relativity, which proposed that the speed of light is constant in all inertial frames of reference, and that time and space are relative concepts. Einstein's theory fundamentally changed our understanding of the universe, leading to new insights into the nature of time, space, and gravity. The Michelson-Morley experiment demonstrated that the speed of light is constant, regardless of the motion of the source or observer, a concept that revolutionized physics and our perception of the universe. This experiment not only disproved the ether theory, but also paved the way for the development of modern physics, influencing countless scientific advancements that followed. In the early 1900s, Russian physiologist Ivan Pavlov embarked on a series of experiments that would make him a household name. Pavlov was originally studying the digestive processes in dogs, but a chance observation led to a groundbreaking discovery that would forever change the field of psychology. Pavlov noticed that the dogs in his lab would start to salivate not only when food was presented, but also at the sight of the lab assistant who fed them. Intrigued by this observation, Pavlov designed an experiment to investigate further. He decided to pair the presentation of food with a neutral stimulus, such as the ringing of a bell. After several repetitions, Pavlov found that the dogs began to salivate at the sound of the bell alone, even when no food was presented. Pavlov concluded that the dogs had learned to associate the bell with food, leading to a conditioned response of salivation. Pavlov's discovery of classical conditioning demonstrated how behaviors can be learned through association. This principle has had a profound impact on behavioral psychology, helping us understand how learning and behavior are influenced by our environment. Classical conditioning has since been applied to various fields, including education, therapy, and behavior modification. Pavlov's work laid the foundation for the study of learning and behavior, influencing subsequent research and theories in psychology. His experiments with dogs revealed the fundamental principles of classical conditioning, showing that even simple organisms can learn complex behaviors through association. Pavlov's legacy continues to inspire psychologists and researchers to this day, highlighting the importance of observation and experimentation in scientific discovery. In 1909, American physicist Robert Millikan conducted an experiment that would become one of the most famous in the history of science. The Millikan Oil Drop Experiment aimed to measure the electric charge of a single electron, a fundamental constant of nature that had eluded precise measurement. Milikin used an apparatus that sprayed tiny oil droplets into a chamber between two electrically charged plates. By adjusting the voltage across the plates, Milikin was able to balance the gravitational force pulling the droplets down with the electric force pushing them up. This allowed him to measure the charge on each oil droplet with remarkable precision. Through careful experimentation, Milikin discovered that the charges on the oil droplets were always multiples of a smallest, consistent value, which he identified as the charge of a single electron. He determined this value to be approximately 1.6 times 10 to the minus 19 coulombs. Millikan's precise measurements provided crucial evidence for the quantization of electric charge and supported the atomic theory of matter. His work confirmed the existence of electrons as discrete particles with a specific charge, a major milestone in the development of modern physics. The Millikan Oil Drop Experiment earned Robert Millikan the Nobel Prize in Physics in 1923 and advanced our understanding of the fundamental properties of electrons. This experiment not only confirmed the quantization of electric charge but also provided a deeper insight into the structure of atoms, laying the groundwork for future discoveries in atomic and particle physics. In the 1950s, psychologist Solomon Asch conducted a series of experiments that revealed the powerful influence of social pressure on individual decision-making. Known as the Asch conformity experiments, these studies explored how group dynamics can lead individuals to conform to the majority opinion even when it is clearly incorrect. Participants in Asch's experiments were asked to identify which of three lines matched a target line in length. However, unbeknownst to one true participant, the other members of the group were Confederates instructed to give incorrect answers in some trials. Asch wanted to see if the true participant would conform to the majority's incorrect answers. Asch found that a significant number of participants conformed to the majority's incorrect answers at least once, even when the correct answer was obvious. This demonstrated the powerful influence of group pressure on individual judgment and decision-making. The experiments revealed that social influence can lead individuals to doubt their own perceptions and conform to group norms, even when they know the group is wrong. Asch's findings highlighted the importance of social dynamics in shaping behavior and decision-making. The Asch conformity experiments have had lasting implications in social psychology, particularly in understanding group dynamics, peer pressure, and the power of social influence. Asch's work has informed research on conformity, obedience, and group behavior, shedding light on how individuals are influenced by their social environment. In the 1950s, American psychologist Harlo conducted groundbreaking experiments on attachment and maternal bonding using rhesus monkeys. Harlo's work revealed the profound importance of emotional and physical comfort in the development of healthy attachment and social behaviors. Harlo separated infant monkeys from their mothers and provided them with two surrogate mothers, one made of wire that provided food, and another made of cloth that offered comfort, but no food. Harlo wanted to see which surrogate the infant monkeys would prefer. The infant monkeys showed a clear preference for the cloth mother, clinging to it for comfort and security, even when the wire mother provided food. This demonstrated that the need for emotional and physical comfort outweighed the need for food. Harlo's experiments demonstrated the importance of nurturing and emotional support in early development. The monkeys that were deprived of comfort and attachment exhibited severe social and emotional deficits, highlighting the critical role of maternal bonding. Harlo's work significantly influenced the field of developmental psychology and informed practices in caregiving and childcare. His experiments underscored the importance of comfort, security, and emotional support in the healthy development of infants, shaping our understanding of attachment and bonding. From the late 19th to early 20th century, Hungarian physicist Lajos Aos conducted a series of experiments that tested the equivalence of inertial and gravitational mass. This principle is a cornerstone of Einstein's theory of general relativity, which describes the gravitational interaction between matter and spacetime. Aos used a torsion balance, a highly sensitive device that measures very small forces. The device consisted of a horizontal bar suspended by a thin wire, with different materials attached to each end of the bar. By observing the twisting of the wire, Aos could measure the gravitational attraction of the materials and compare their inertial mass, or resistance to acceleration, and gravitational mass, or attraction by gravity. Aos's experiments involved measuring the gravitational attraction of different materials, such as lead and aluminum, to determine if inertial and gravitational mass were equivalent. He conducted these measurements with incredible precision, showing that the two types of mass are equivalent to within 1 part in 20 million. The confirmation of the equivalence principle was a significant finding, supporting the idea that gravitational and inertial forces are indistinguishable from one another. This principle is a cornerstone of Einstein's theory of general relativity, which revolutionized our understanding of gravity and the structure of space-time. Aos's work remains fundamental in the field of gravitation and has influenced countless studies in physics. His precise measurements and innovative techniques demonstrated the power of careful experimentation in advancing scientific knowledge. The Aos experiment continues to be a benchmark for precision experiments in physics, highlighting the importance of the equivalence principle in our understanding of the universe. In the 1970s, psychologist Walter Mischel conducted the Stanford Marshmallow Experiment, a study that would provide valuable insights into self-control and delayed gratification in children. This experiment aimed to understand how the ability to delay gratification could influence future success and behavior. The setup was simple but effective. Children were given a choice. They could eat one marshmallow immediately, or wait for a short period and receive 2 marshmallows. Researchers observed how long each child resisted the temptation to eat the marshmallow and recorded their behavior. The results were fascinating. Some children were able to wait patiently for the promised reward, while others succumbed to the temptation and ate the marshmallow right away. Mischel followed up with these children years later and found that those who had demonstrated the ability to delay gratification tended to have better life outcomes, including higher academic achievement, better emotional regulation, and lower rates of substance abuse. The Stanford Marshmallow Experiment highlighted the importance of self-control in achieving long-term goals. It provided valuable insights into the role of delayed gratification in personal development and success. Mischel's findings have had a significant impact on educational strategies and psychological research, influencing how we understand and foster self-control in children. The Stanford Marshmallow Experiment demonstrated that the ability to delay gratification is a crucial skill that can predict future success and well-being. Mischel's work has informed educational practices and psychological interventions aimed at improving self-control and impulse regulation. This simple yet powerful experiment continues to inspire research on the importance of patience and perseverance in achieving long-term goals. In 1820, Scottish chemist Sir Humphry Davy and his assistant Michael Faraday conducted a series of groundbreaking experiments that would lay the foundation for the development of modern refrigeration and cryogenics. Their work focused on the liquefaction of gases, a process that would have far-reaching implications for science and industry. Davy and Faraday's experiments involved passing electric currents through various gases to observe the conditions under which they could be converted to liquids. They discovered that certain gases, such as chlorine and carbon dioxide, could be liquefied under specific temperature and pressure conditions. Their work demonstrated that gases could be transformed into liquids by manipulating temperature and pressure, a principle that would become fundamental to the field of thermodynamics. The ability to liquefy gases opened up new possibilities for storing and transporting them, leading to significant advancements in science and technology. Davy and Faraday's experiments laid the groundwork for the development of refrigeration technology, which has numerous applications in food preservation, medicine, and industry. Their discoveries also paved the way for the field of cryogenics, which involves the study and application of extremely low temperatures. The principles discovered through the Davidson experiment are fundamental to modern cryogenics and refrigeration. Davy and Faraday's work demonstrated the power of scientific inquiry and experimentation in advancing our understanding of the natural world. Their contributions have had a lasting impact on science and industry, highlighting the importance of innovation and exploration in driving progress. In 1954, French physicist Maurice Allais conducted a series of experiments that would spark debate and further research into gravitational theories. Known as the Allais effect, these experiments aimed to observe the motion of a pendulum during a solar eclipse to detect any gravitational anomalies. Allais used a paraconical pendulum, a type of pendulum that can move in any direction. He meticulously observed its motion during a solar eclipse, noting any deviations from the expected path. To his surprise, Allais reported anomalies in the pendulum's motion during the eclipse, suggesting that gravitational effects during these events could be different from those predicted by Newtonian physics. The Allais effect generated significant interest and controversy within the scientific community. While some researchers confirmed similar anomalies in subsequent experiments, others were unable to replicate Allais' findings. This lack of consensus sparked ongoing debate and further investigations into the nature of gravitational forces. The Allais effect has continued to intrigue researchers, prompting them to re-examine the fundamental principles of gravity and explore potential new physics. While the exact cause of the observed anomalies remains uncertain, the experiments have inspired innovative approaches to studying gravitational interactions. The Halley effect challenged existing theories of gravity and highlighted the complexity of gravitational interactions. Maurice Halley's work demonstrated the importance of questioning established scientific principles and exploring alternative explanations. The ongoing research inspired by the Halley effect continues to push the boundaries of our understanding of the universe, showcasing the dynamic and ever-evolving nature of scientific inquiry. Archaeological excavations at the Cahokia Mounds site in Illinois have uncovered evidence of a complex pre-Columbian society, revealing the sophistication and achievements of early North American civilizations. Known as the Cahokia Mounds Experiment, these investigations have reshaped our understanding of the cultural and technological advancements of ancient societies. Excavations and studies conducted in the 20th century revealed large earthen mounds, urban planning, and artifacts indicating a highly organized society. Cahokia was one of the largest and most complex urban centers in North America before European contact, with evidence of advanced agriculture trade networks and social hierarchy. Researchers discovered that Cahokia was a bustling city with a population that rivaled some of the largest cities in Europe at the time. The city's inhabitants constructed massive earthen mounds for ceremonial and political purposes, demonstrating remarkable engineering skills and a deep understanding of their environment. The Cahokia Mounds experiment also uncovered evidence of sophisticated agricultural practices, including the cultivation of maize and the use of raised fields and irrigation systems. These techniques allowed the city to support a large and thriving population, highlighting the ingenuity and adaptability of its inhabitants. The artifacts discovered at Cahokia, such as pottery tools and ceremonial objects, provide valuable insights into the social, political, and religious life of the society. These findings challenge previous assumptions about pre-Columbian civilizations and highlight their cultural and technological achievements. The discoveries at Cahokia Mounds have reshaped our understanding of early North American civilizations, revealing their complexity and sophistication. The Cahokia Mounds experiment has provided a deeper appreciation for the achievements of ancient societies and their contributions to human history. These findings continue to inspire archaeologists and researchers, emphasizing the importance of preserving and studying our cultural heritage.